Hey, everybody, welcome back to part two of our interview with Paul Reese. Thank you for listening. Henry, you want to kick it off?
Yeah, I'll try to be a little bit of a timekeeper here because we're fortunate enough to have Paul and Paul Reese with us, who has written several papers. Many of them I'm a huge fan of. Almost all of them. I would say all of them, for sure. And there's some that Paul has done on end of period reliability that we touched on in the last segment here. And there's a lot on where we talk about TUR. And when Ryan and I reached out to Paul to come on the podcast, we talked, what do we have to talk about was one of the jokes. But if you know Paul, we can talk. And that first segment went a bit because these topics are fascinating, and it's just the knowledge that the encyclopedia that Paul is it's just awesome to be able to talk about it. So a little bit of recap. We gave some examples in the last part of the Hubble telescope and the Spirit of Kansas B2 bomber. Talked a little bit about the right processes, the right procedures. Talked a lot about temperature measurements and kind of set the stage with that. And Paul mentioned end of period reliability. So that's something near and dear, at least to me in my career, is we talk to people, set this up, and you talk to people and their measurements are good. All of a sudden they have a failure. And we know they had a failure. We know the instrument is shifted. And what do they do after the failure occurs? Do they analyze that end of period reliability? Do they consider stability in any of this stuff in their uncertainty budget, or when they're accounting for the risk? Do they look overall that says, hey, I have this device that every other calibration it's failing, or every calibration the provider's adjusting it, and then it's rinse repeat, right? It comes back into the lab a year later or 6 months or whatever the interval is. It comes back in and it's another failure. And it's just another and another and another. And you could say, hey, they didn't buy the right. Did they know the right requirements when they sourced the system? What are they doing with it? And it all comes out to that reliability aspect of things that you should be looking at. If you have multiple failures on something, the chances are that instrument's not good enough, or the chances are you need to shorten the calibration interval, at which point it might make a lot more sense for the end user to just buy better equipment. So
Mm-hmm.
it all feeds into the knowing the right requirements, which there's various pieces of end of period reliability. We talk about, what do I want to measure? How do I want to control my PFA and PFR, which were probability false accept, probability false reject. The one is I'm going to send something out that I say is good, that's actually bad. And the other one is I'm going to call something bad that's actually good. So those two, and that's that's calling something bad that's actually good as PFR, right? And then calling something bad that's actually, did I get that right? I'm going fast. And calling
Yeah, yeah.
something calling something good that's actually bad is is a PFA scenario. So I think
Yeah, yeah.
I do that fast and I get tripped up in my own head. But let's start with that, Paul, on because you mentioned it. Let's start with end of period reliability and how much that matters and what it is.
Yeah, it's a great question, and there's different, we even now in the 20, first century, we still use a variety of vernacular of words that some people call something one thing, some people call it the other, and then really they mean the same thing. So end of period reliability is essentially, how often that an item is found in tolerance when you calibrate it. And we are talking about, calibration and verification because we're verifying that it meets specifications. So you send something to NIST for calibration, they're not going to issue a pass fail statement. So
Nope.
that's the verification process, right? So does it meet specs or not? So the end of period reliability, Greg Sinker, who I know you guys probably both know. I know Greg's a super great guy, just a monster intellect guy that I really enjoy talking to a lot. And Henry and I are fortunate enough to chat a good deal with him, with Greg at the last NCSL meeting. But Greg and I have spoken in the past how if you had to pick all these important things in metrology, end of period reliability arguably is the most important metric or number that you can really focus on. And that's true for a number of reasons. Some people might say, well, no, it's your test uncertainty ratio. Test uncertainty ratio,
Mm-mm.
that's what really controls risk. And really they both do, right? Trying to actually compute false accept risk or false reject risk, you need to kind of know both of those things. There's no way to do it without both of them. You can put limits if you know test uncertainty ratio. You can put limits on what your risk is, or if you just know end of period reliability, you can put limits on it without knowing test uncertainty ratio. But the reason that end of period reliability is so important is if you think about it like this, we talked a lot in the last bit here about control charts. So a control chart really is just a series of calibrations that are almost back to back, maybe minute to minute, hour to hour, day to day, week to week, whatever it
Can be.
is. Yeah,
Mm-hmm.
it can be. So if you look at your reliability history, maybe you calibrate something once per year, and you look at the last 5 years, you might have 5 calibrations of it. But that's still, you can do a control chart that way. So, but if you did have the advantage of having a long history and a control chart of your end of period reliability, how often is it found in tolerance? And that's over a long enough period of time, so long that many different technicians have calibrated it. They've used different standards when they calibrated it. They, your own standards that they're using have been recalibrated by NIST or whoever it is. Ryan mentioned in the last section, maybe use different calibration providers sometimes than. So if you have really lengthy, really comprehensive end of period reliability, even your laboratory effects, the temperature of your lab, its effect is going to be already contained in that end of period reliability. And Dr. Dennis Jackson and John Harbin with Keysight, they and Howard Castro and many other people have written papers on how really full on reproducibility, which is to say an end of period reliability from a control chart, if it's
Yep.
comprehensive enough, that is your measurement uncertainty. That is your total measurement uncertainty. You don't need even NIST traceability. You don't need anything because NIST traceability is baked into that end of period reliability. So is the influence of your lab. So is the influence of resolution of your standard and your unit under test. All of these components of uncertainty that we usually put into a measurement uncertainty budget are reflected in an end of period reliability analysis and a control chart if you've got enough data, you know. And so what that really shows you, Henry, you mentioned before about, maybe an item's not good enough or an item's not accurate enough, or maybe its specification is really good, but it doesn't meet that specification often. So its end of period reliability is poor. And so what that really tells you is that, well, that specification is not a 95% confident specification. It's like a 62% confident specification. If you
Right.
want a 95% confident specification, knowing enough history, knowing that it only met plus or minus 1%, 62% of the time, you can say, well, then if I want a 95% confidence, the real number is more like 1.7% or something. And you can put a more realistic specification on something.
You
So,
can always backtrack the numbers, and that, yeah, if you're shooting for the higher you're shooting for, the more samples you need. So we're talking about the total number of intolerance attempts, right?
yep,
Results. If we're doing control charts, every intolerance control chart that we're measuring, assuming we have our process set up, what we're talking about relies a lot on we have the foundational pieces. Our process is under control, and that's what we're showing with our control charts anyway, right? But we're relying on that because if you're just starting to take control charts, you don't know if your process is in control or not.
that's right.
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 So that's where you need to get to like a baseline of, I need to like 5, 6, 7 really good measurements to start making me feel good about what's happening. But if I wanted 95% end of period reliability with 95% confidence, I need like 58 in a row in the intolerance readings. And this is there's a lot of importance to this because the cal lab that does your calibrations, you're switching labs. Ryan mentioned it. I love the thought process here, but make sure you're switching to an equivalent lab, right? Because
key.
their labs, like you could say, and I hate saying this because I love the company, but uh, um, uh, and I don't think it's bad, but anyway, it's like Fluke. Fluke has primary labs all over, but not every Fluke lab is a primary lab. So if you're going to a primary lab and you're going to switch to another lab, make sure they're also a primary lab. right? And that's just the way it goes. Make sure it's an apples to apples comparison. Don't add into the mix a fly by night organization that can do it for, $20, and then your expectations are going to be completely different. And I think everybody knows that. Just make sure you're going to equivalent labs. And a lot of people NIST, traceable SI through NIST, the Joseph Junction arrays that NIST have. There's a lot of labs out there that have Joseph Junction primary standards. So if you were going to NIST and want to change it up, find another lab with it and make sure they're going to do it on the Joseph Junction, because a PO that says please calibrate with primary standards sometimes does not get that done. I mean, you have to specifically, it's not on their sheet. A lot of these labs, it's just going to be a standard cal. It's usually, I think Keysight calls it the gold calibration service or something like that. So maybe there's a platinum one out there. So if you're getting gold, find another lab that's and different labs are going to, I hate babbling on this, but one lab's gold is another lab's platinum. So yeah, you just have to really look at that, the measurement capability there on that. So I'm going
to. You touched on something, and I'm sure you deal with it all the time, at Morehouse, being one of the premier, commercial labs for force and stuff. So this idea of you issue a PO and you just, because we outsource some stuff, which we don't have the capability. We don't, at the company I work for now, and we're pharmaceutical, so we don't do any RF or microwave. So the little bit of stuff that gets submitted to us, we farm that out to a commercial lab, and so so the devil's in the details, right? So all of these things that you can blindly assume that they're going to do, that they're going to have good test uncertainty ratio, and that they're going to, actually meet if they are accredited lab, they're going to meet what their, accredited tolerances are, all of these things are assumptions that are easy to make. And then you get it back and they didn't do something that you expect. Oh, this thing was 98% of its tolerance. They didn't adjust it. Oh, what a bunch of idiots. Well, did you tell them if it exceeds a certain point? All of these things we can go back and forth between Cal Labs and customers and talk about, well, you should have known. Well, like the B2 thing, well, you could have just written that down, and then
how do we know?
Assume and, just guess, and all of these things, Yeah.
UCAS LAB 48 says you're supposed to tell the lab, right? And then ISO 376 says during contract review, this should be uncovered. And I'm like, no, this should be uncovered when you're quoting.
Yeah.
Right. And making sure all the things are there. Contract review should just make sure the sales orders and the purchase orders, that everything's aligning between the two companies, that what we've agreed on during that quoting process is the exact same thing that was submitted for calibration. And that irks me a little bit, but that's it. When you're talking to somebody, where is the adjustment criteria? Is it at 80%? Is that at what risk level are you okay with? And UCAS LAB 48 says you should say, Paul, I'm okay with 10% PFA. Paul's done all his analysis. That's okay. That's that probability of false accept that's we're looking at. And then it's like, how are you going to measure it? Are you using, there's so many things after this, but those discussions should absolutely be crystal clear up front in the during the quotation stage. And the problem in industry with this is guess what happens in the quotations? People have purchasing officers that are not educated on anything that they need metrologically. They're just like, some guy gave me this or some gal gave me this, and now I got to take care of it. Can you calibrate it? Well, yes. However, and then I don't know.
Going back to the BIM, what do you call calibration?
Yeah. Well,
to them, like a purchasing person, they're going to make it perfect. They're calibrating it, We're
going to send it to you. Force is I talk about it before, very mechanical in nature. If you don't have the right, adapters that you're using with it, you could get an S-beam load cell, very simple. There's 4 different answers depending on the way you load it. Through the threads, both ends, flat both ends, through thread one end versus the other. It's 4 scenarios. It's huge, vastly different results.
Oh yeah, we showed that in the school. You showed that, you demonstrated that in the school. So those of you in the school, you can go and watch Henry's videos. Simple things make a big difference.
Simple things, and no one thinks about it, right? So, and that's okay. So that's a good example of end-of-peer reliability. You send it to another lab. Lab 1 talked to your technician 10 years ago, and they've been doing the CALs for 10 years, and they have notes in their system, so they don't need it on your PO, that they know you're going to load your S-beam through both threads. The other lab decides they're going to load it flat. You have an out of tolerance and you're like flipping out about it. And it's like, okay, well, no one told that other lab. The other lab's equally as good. No one told them how to load it. It was just that engineer or the tech that talked to X lab 10 years ago that figured out how you were using it, because somebody currently, that person's long retired, and the purchase order says, please calibrate.
Yeah.
Yep.
No, those are great points, and kind of harkens back to this idea that, how you calibrate it is kind of dictated by your procedure, and that
Mhm.
measurement uncertainty that you're assigning to these values that you're providing to customers, that measurement uncertainty really does depend on all of these detail type things that you're bringing up. And I'm sure that, there's a ton in the forced world, all these, the fixtures and the alignments and, different things that you can do. And so sometimes you need to know, well, how are you going to use it to be able to say, well, then this is the appropriate way to calibrate it. If you don't know, there's just a million things out there in
So
different
many
measurement disciplines that have to be known.
indicators. You get into
Yeah.
cables, 4 versus 6
Yeah.
wire. You get into somebody accidentally indicators that don't have lockouts. Someone accidentally
Yeah.
erased something. Indicators that don't ship well. We have those all the time. There's a great indicator that's out there that I love it to death. Though if you bump it during shipment, the card comes loose and all the data, you lose all your data. So that,
Yeah.
I mean, that's when you're that segues us into choosing the right equipment, right? You start looking at that. But with end of period reliability, it is really everything. The number of intolerance to calibration. And I have a few points here, Paul, you can add to or whatever, but like generally reliability will decrease after time. So as soon as the lab does it, and remember, they're doing it under their conditions, not your conditions. So that's another uncertainty piece to discuss. But as soon as they do it, it starts decreasing from that as soon as they cal it from that day on. And then there's the other, you need to figure out how much testing do I really need? We threw some numbers out to start being confident with the measurement. And then there's the term that they use in several standards, that a priori knowledge of the measuring and test equipment. Like
Yeah.
if I know, we started talking about model numbers. If I have a 3458A, I have a pool that someone's given me, Navy or somebody else, someone's talked to, and they say, hey, on average, your 3458s we had cal every year, they're 90% reliable, right? I'm
Yeah.
making up numbers. They might be, I'm just throwing numbers out there. I had no idea on the 3458A. I do have some idea because I know Mr. Sanker had 7 of them, and he did some studies on those versus some other ones. But yeah, if you find, hey, they're 90% reliable, that's some knowledge, but is that the way you're using it and your knowledge? I mean, that's the some of these other discussion points here. Are they not? And how do you treat? So I'm gonna go into the other one that's gonna get us into some tolerance stuff. Is what do you call? How do you treat intolerance? Is it the tolerance plus the measurement uncertainty? They're different rules here for end of period reliability. And Paul, I think you can elaborate a little bit on those, because we've talked numerous times about this.
Yeah. So, like, I think what you're getting at is, guard banding, what do you consider something intolerance? Does it have to be intolerance by an amount, equivalent to the uncertainty of the measurement process, which is certainly if you're going to limit the false accept risk, but you are going to drive false reject risk up, high if that's your guard band. I think I'm probably going to shy away from the global versus specific risk, because that is while it's super important, it's really difficult to cover that aspect, I think, in a short
We
form.
deal with that in there's a later episode for those that are listening and watching coming up, that Ryan and I talk about global versus specific with Star Wars examples and super nerdy stuff for.
Yeah. Yeah, but I think that, the acceptance rules is, again, another thing that should be documented in, contract, when you submit something for calibration, for sure. It's an interesting thing, and I'm glad it kind of popped back into my mind when we were talking earlier about contracts and outsourcing in labs. This happened to me, and it blew my mind the first time this happened. This is a 100% true story. I probably on my laptop got the documents to show it, but we had sent a gauge block out when it was a previous company, but we'd sent a gauge block set out for calibration, and to a class tolerance, right? So these class tolerances are, this set has this specification. If it's, and I'm not a gauge block guy, but I think they're, what is it, class, I don't know. Anyway, they have class tolerances. So we sent it out, and let's just say that the specification on the 1-inch gauge block in this set to meet class tolerance was, and they may be asymmetric, but let's just, for sake of argument, say there's plus or minus 10 microinches, right? So we send them out, we say, calibrate it to this specification and, all the other stuff that goes with it. and so they send it back, and one of the gauge blocks in there has a value, a measured reported value on the cert of like plus 12 microinches, larger than the plus or minus 10 microinch specification.
Mhm.
The cert says that it meets the class tolerance. So I think obviously this is a typo. I'm going to, call the Cal Lab. They're going to issue a revised cert, and they're going to say, okay, it was either out of tolerance, or that wasn't 12 microinches, that was 1.2 microinches, whatever. There's going to be an explanation. But the explanation that they actually gave, which was real, really did blow my mind. And it has to do with acceptance decision rules, right? Like, well, when do you call something intolerance or out of tolerance, and guard banding and all this stuff? So it turns out that the class tolerances, as I understand it, for gauge blocks were kind of established in a federal specification called FedSpec GGG 15C or something like that, right? That was the document that established what a class, whatever gauge block set was. I know there's some ASME specifications, and
Yeah.
but
They
at
do
any
get
rate,
a little confusing there. There's like a NIST classes, and then
that's right, and they
the other one.
changed
Yeah.
over time,
Yeah.
So it turns out in this Fed spec, it had its origins in like the early 70s. It was revised a few times, but it's just so ubiquitous in industry that people still use it. In fact, the lab that calibrated these gauge block sets said it was calibrated, per this federal specification. And so it turns out after a bunch of emails back and forth that the explanation was, and this is true, it's written in this, again, it's FedSpec GGG 15C. I think that's right. That it says in there that yes, plus or minus 10 microinches or the asymmetric limits, here are the class tolerances for this gauge block set. However, you can't measure things perfectly. Revelation, right? There's measurement uncertainty.
Right.
So there's a table in there that says these are the allowable measurement uncertainties for this gauge block set. And it says basically that you don't want to call something out of tolerance unless it really is out of tolerance by an amount equivalent to the measurement uncertainty in this table, which is kind of a reverse guard band, right? It's like
Yep.
what that specification is trying to do is prevent false reject risk. They don't want a lab to reject a gauge block set unless it really is truly out. And so the funny thing is they just give a table that is like an allotment of measurement uncertainty, having no idea if the lab that actually is going to measure this gauge block set is actually going to have that uncertainty or a worse uncertainty or a better uncertainty. It was just a table of uncertainties. And so the explanation was, well, that gauge block set is not out of tolerance because that measured value of 12 microinches that, looks like it might conceivably be out is actually not out by the allowable measurement uncertainty stated in that table. So, and it turns out, yeah, I call some of my other metrology friends that work in the mechanical dimensional thing, and to them, it's like, oh, of course, yeah, that's like replete throughout a lot of mechanical
We have thread
specifications.
plugs.
Thread plugs, gauge plugs, things
Yep.
like that. That's exactly right. Yeah, Jim Waxer actually was the guy that I worked with at Kennedy that turned me on to that, and it just blew my mind. In fact, I fired off an email to Howard Castro and I said, Howard, can you believe this? This is a thing. This happens in industry. It's like it's reverse guard banding. It seems so crazy.
Well, it's if we go to the ASME document, because we're not going to go fully into decision rules, but that would be your relaxed acceptance.
Yeah.
Right. I mean, we're
Yeah.
talking stringent is plus or minus 10 microinches. Anything to take the guard band it by the uncertainty, and maybe it's plus or minus 10 or plus or minus 8 microinches, whatever it may be, and that's your stringent zone. It's
Yeah.
good.
Well,
And the stringent rejection zone is anything over that. Anything over the tolerance is bad. Anything, before we have some risk in the middle between the tolerance and that guard banded limit. But yeah, it's really interesting on that, the relaxed rejection zone. And then the question becomes, Paul, why don't we just make that the tolerance?
well, see, and
Yeah.
that's what I saw this a ton doing thread plugs. So I've done a lot of thread plugs over my years. And what would happen is we would get thread plugs in that would fail, and they were brand new. And so then we reached out to the manufacturer, whoever it was, I can't remember, Vermont Gauge or whatever. And they were the ones that led us onto that you're talking about, Paul, is,
Okay.
the tolerance plus uncertainty is your new tolerance. And I always thought that was wacky, but I was, I'm at the time ask no questions, just do what you're
Well,
told, you know?
it goes full circle with end of period reliability. Do you do tolerant? Do you reject something at tolerance? And this is, I think, a lab's decision where we're going to run it. Do we reject it at the tolerance? Do we reject it at the tolerance plus uncertainty? Do we reject it at the guard banded piece?
Well, you know
And
what
it's
I forgot to add in there. This is where it gets tricky, Henry, is so like those cases where we're trying to reject something that is coming in from brand new, right? But then that customer will take that and be like, well, we bought this brand new, so we'll send it back. But then the manufacturer is measuring it with that rule, that decision rule, and then they're saying, well, we won't give you a refund or a new one, right? And so it gets
Mhm.
into this horrible cycle. Sorry, I didn't mean to interrupt you there, but I wanted to add in that last little part that they do send them off to the manufacturer, who then calls them good, and then it's a lack of trust in because the manufacturer has to be better than the cow lab, right? That's what a lot of times they're thinking. It's like the manufacturer is going to be
well,
perfect on this, you know?
you're teeing up, which we said before, right process, right procedure, right requirements, and choosing the right standards. And now we're talking with Paul about choosing the right standards. We mentioned test uncertainty ratio, which I'm going to poke the bear here a little bit. And Paul knows I'm going to poke him on this one because we already said it. It's nothing new. But test uncertainty ratio, what goes in? So we have the top general span of the tolerance at the top. Now, what goes in that divisor? Some people can confuse this with, we talk TAR, they confuse it with test accuracy ratio and everything else. But generally, the debate on that bottom is my calibration process uncertainty. What does that include? That includes the calibration and measurement capability of the lab. That often includes the repeatability of the UUT, right? That includes any environmental influences. Could include some other things. We just say other, but the big topic of debate, the poking the bear, is does that include the resolution? And Paul has a great story about this, which does that include the resolution of the unit under test? Because someone submits something and it has a really bad resolution, the repeatability a lot of times is almost perfect. So that being said, Paul, what are your thought process on this, or enlighten us with the Jerry Hayes story that is also awesome?
Well, yeah, so just so many thoughts about it, but yeah. Uh so this idea of what goes in the denominator, right? And it really depends on, well, do you have a really staunch, official, hardcore definition of test uncertainty ratio that you're working with, right? And so in Z540, it was the expanded measurement uncertainty. And so expanded measurement uncertainty, then you got the gum and and again, I know that there's, people in industry, good friends, I would say, where we have, some differing opinions on this. And so I would say this is one of the most controversial issues in the metrology and calibration world right now, and one that really needs a definitive answer because it affects accreditation bodies, it affects the way standards are written, it affects a lot. And so I think we need to get this right. But so the idea that Henry's talking about, and I've been on both sides of this fence. I have been on the side that I would say that I disagree with right now, and I was staunchly on that side. So what I think Henry's talking about, and for those that don't know, Jerry Hayes is like one of the greatest, he's unfortunately passed away.
92, I
Uh,
believe, right?
yeah, Jerry
Yeah.
had a good run, and he had a major monumental influence on the metrology and calibration world, and is generally looked at as the father of the 4-to-1 test uncertainty ratio, and many other things, and wrote for the Navy the Standards Laboratory Information Manual, the SLIM, and was really the godfather, and just laid out the groundwork for everybody that we all have kind of passed in his slipstream. I would say him and a lot of other guys. But anyway, so the story Henry's alluding to is, I was of the opinion many years ago that, yeah, your measurement uncertainty is like the uncertainty of your standards and your process. The unit under test is simply the thing that you are testing, and no aspect of the unit under test should contaminate my pristine measurement uncertainty. I'm a very proud metrologist. I have these very expensive systems, and I take great pride in my work. And so don't you dare impugn my measurement uncertainty, especially when it's going to be used for a test uncertainty ratio, by making me include aspects of the unit under test. But Jerry Hayes and Del Caldwell were two great lifelong friends, and they had a lot to do with the writing of Z540, both versions, the Z540.3, the one in 2006, and the handbook and all of this stuff. And so during the development of that handbook, we were all talking about this subject, and I could not believe that they were suggesting that when you compute a test uncertainty ratio, that in that denominator, in the uncertainty, that they would make you put aspects of the unit under test like resolution. And so the thought experiment that I came up with that I thought was so definitive, and I told Henry I was like ready to jump up and down on top of the desks and say, Jerry and Dell, what don't you guys get about this? Like, if what you guys are saying is true, if I have an old Simpson 260 analog voltmeter with an analog scale on it or a mechanical meter movement, and between minor divisions, I have some resolution that that limits what I can know that that meter is actually reading. I have to interpolate. I have visual acuity and all this stuff in between minor divisions. I said, on a best case, let's say that you could interpolate on a 10-volt scale to 100th of a volt or something like that. You're going to make me take that resolution that is an aspect of the unit under test, put it in my test uncertainty ratio, and I no longer have 10 parts per billion of my Josephson voltage system to your 2% accuracy specification of this meter, which would give me, 100,000 to one, some ridiculously astronomical high uncertainty ratio. System costs, $500,000 and your meter costs $200. But you're telling me if I have to include the resolution of the unit under test, that I have like a 2 or a 3 to 1 test uncertainty ratio. And they both nodded. And I'm like, you're out of your mind. We can't even have a conversation anymore. This is ridiculous. I thought you guys knew about metrology. What are you saying? Do you understand how insane the words coming out of your mouth are? And so that was how I felt at the time. And this was we were having a committee meeting at the NCSL conference, and I was there with a bunch of NASA folks, my boss, managers, people that I'd reported to and stuff. And so I went back to my hotel room and I thought about, like, these are not dumb guys. Like, these are some of the brightest guys and the guys that laid everything. So I can't just call them crazy. I've got to figure out what the hell they're talking about. And so the idea or the little thought experiment I came up in my mind in my hotel room that night was this. It's like, so I thought about, if you have like $1 million gauge block, the best gauge block in the universe that the length of, it's perfectly parallel, there's essentially zero uncertainty. And then you take a unit under test caliper and you put it on this gauge block and you do everything correctly, everything's clean, you get the best lab in the world, it's plus or minus 100th of a degree, and one technician sets this caliper or this micrometer on this gauge block, and they turn it and the clutch engage it, all this stuff. And technician A reads this micrometer and says, I think this micrometer reads this. And he writes that number down. And he says, and I'm going to say that that's intolerance. It's close, but that's intolerance. Now, nobody touches anything. The room doesn't change. The gauge
Now
block.
he could do it. Yeah, he could do it 10 times and get that
10
number.
times, same number. He writes it down, he looks at it, same number. Technician B comes up, looks at the same micrometer. Nothing's changed. The micrometer's still placed on the gauge block. Nothing has changed. And technician B, she writes down a number and she says, this is what I think this micrometer reads. And it's close, but it's barely out of tolerance. So 2 technicians have written down 2 different numbers and came to 2 different conclusions. One says intolerance, one says out of tolerance. So there is measurement decision risk here. We cannot make a confident decision. And yet we have a lab that's controlled to 100th of a degree. We have a gauge block we paid $1 million for. NIST themselves said that's the best gauge block in the universe. So where is the measurement decision risk coming from? I mean, if the micrometer has an accuracy specification of, I don't know, 50 microinches or something like that, and our gauge block has, 1 nanoinch, don't we have like 1,000,000 to 1 test uncertainty ratio? That's what I would have said before. But I started to see that this is what those guys were talking about. We don't have 1,000,000 to 1 test uncertainty ratio. We have measurement decision risk here, and arguably measurement decision risk, that is false accept, false reject, is the only reason in the universe to maintain any type of test uncertainty ratio, or to even have that be a phrase, or to even use that term. If we're going to talk about test uncertainty ratio and people say, well, why do you have that? Why do you want 4-1 or 10-1 or 2-1 or 100-1? Well, I want to know that when I make a pass or fail decision, that that's the right decision. Then you got to include aspects of the unit under test, because none of this measurement decision risk originated with my process or my lab or anything else. It originated from the finite resolution of the unit under test. So Ryan, in PRTs, if you're measuring something and you're measuring a customer's, thermometer that's in there, and you got it in 100-degree bath, and it's got a plus or minus 1 degree accuracy, so anywhere from 99 to 101 degrees is going to be intolerance. But the thing is sitting there and it's reading, sometimes it's reading 100.98, 100.99, 101.02. 99.97, right? Well, you got a great bath. You got 5 of your best PRTs in there. You just calibrated them by all the fixed points in your lab. You just got done writing the check for your, $3 million worth of temperature standards. And yet this item has got noise in it. It's, whether it's the digital indication or whether it's an aspect of the cheap element that's in this thermometer that this customer submitted to you, this unit under test is fluctuating. It's got noise associated with it. But I say, Ryan, I am paying you a lot of money. I want you to tell me pass or fail. Now, are you going to feel confident doing that? Whatever you say, there's a chance that you're going to be wrong, right?
Right.
And it has nothing to do with your lab. Now, there are others, and
Unless he's using non-binary. Let's not go there.
yeah, which
You're getting
arguably
evil today, Henry.
Can be evil.
it might be the right thing to do. I mean, some would argue that let's just stop issuing pass fail statements. Let's issue, we think this to this confidence level, right?
Yep.
But quality people in the whole world and the inertia of history, and it demands certainly quality inspectors and all this kind of stuff in industry. They want to know, does this meet its specification? And sometimes you cannot give them that information because the aspects of the unit under test preclude you making a confident decision. And so in that regard, those aspects should be included in the measurement uncertainty, which will tell you that, yes, there is some measurement decision risk here. And it doesn't have anything to do with you don't have good enough standards or people or lab or process or technique or procedure. So that's it in a nutshell.
That's a good nutshell.
it.
And it keeps people honest too. I mean, to some extent, because I alluded it to earlier. Hey, I've seen a perfect certificate. I cannot believe I saw one issued, but I sent it to Ryan because we were joking about it. But somebody had a course resolution, and guess what happens when the resolution's course? Everything is perfect,
Mhm.
right? Therefore, it's like I have no error. I have nothing, right? I just set a course. So that opens the door for the discussion that to end with in this, which is probably a little bit lengthy discussion, is we've gone over the resolution. That makes a difference, right? In picking our standards. Like if somebody we want to know about the repeatability aspect of things. If there is noise in the system, someone could brag that they had the utmost resolution. We can read to the 7th decimal place, but if it's all noise up to the 5th decimal place, is that really, a good system to choose? So
Right.
It really branches into, we talked about TUR, the different ratios. You alluded on the 4-1, which I wanted to make a comment on. For those that haven't read it, and we don't have time to get too involved with it, but Paul and John Harbin, I believe it's risk mitigation strategies, right, Paul? Is that the name of the paper?
Yes.
So Paul did a lot of work on end of period reliability and TUR, and the magic number, surprisingly, how close Jerry Hayes actually came with his 4-1 is to limit risk is 4.6 to 1, and that's alluded to in the paper. That but segueing in, people can read that paper independently. But segueing into this, when we're talking about calibration standards, because a lot of the people out there are like, well, how do I choose them? Management gives me X number of budget. Some salesperson comes in and says, this will do this. I've calculated that I have a 4-1 TUR. I'm more than happy with that number. Is that good enough for a standard?
Yep.
Right. And how do we really look at in choosing those standards? What's going into that 4-1 ratio? And I think what the stuff that I found that I've been working with Greg on is the answer is maybe. right? Is we're showing things where a standard's 2 to 1, and that a company might have bought, and they're rejecting $1 million worth of they're calling $1 million worth of product bad when it's actually good.
Yeah.
And manufacturers run into this, right? If they choose this, and they don't know what they're not all metrologists, they don't know what they're doing, so they buy something that's twice as good and figure it's good. They buy something that's 4 times as good, and now they have $100,000 that they're rejecting per year. But the summation of it is, if they would have bought something, and you have to run all types of calculations on this, but and you have to know the specs and everything else that you're calibrating. But sometimes if you buy the best, right, you're gonna that could what Greg and I showed, if the person actually would have bought a fluke 8588 in this case, they would have been down to less than like $1,800 or something so low out of the million. And right now, currently, they're rejecting $1 million a year. If they would have spent an extra, $14,000, $13,000 on their equipment, they'd be down to rejecting that, $1,800 a year. If they would have spent
Yeah.
an extra $6,000 on equipment, maybe it goes down to they're rejecting $100,000 worth. And this comes up more of the manufacturing. It comes up in a lot of rework in your labs, because if you're rejecting, if your PFR, the probability of false reject, or Paul would say false accept risk. That's another. We have so many terms to say the same thing.
Yeah.
But yeah, and then on the TUR one, the JCGM 106 got the TUR's been so convoluted over the years that they just started calling it measurement capability index. But back to
Yeah.
back to the calibration standard side, I want to get that in there. But back to the calibration standard side, there's pros and cons to all of this, right? You can over purchase for your requirements, and you can under purchase. And I tend to lead. This is another way, and want Paul to talk. I tend to lean, and if you don't know, over purchase. But maybe
Absolutely.
that's not the
I think in
but
general, if you're going to have a default, because, and you made a great point before when we were chatting at one time, sometimes just the analysis alone could take up so much time that you might
Mhm.
spend, $75,000 in engineering labor just looking in and digging in and figuring out what is the minimum acceptable meter, the cheapest meter that I can buy and still just do my job. Where if you'd have bought a
Mm.
3458, you might have spent, or all of the high-end
Yeah, they're all,
800 out there, you spend 15 grand, you just be done with it. And the
Mhm.
advantage that overbuying gives you, and I'm not in the equipment manufacturing business, I'm just saying is that as an engineer or something, if you overbuy and you buy an instrument that is way better than you need, you can always derate it and calibrate it to, less accurate specifications. And then you have the advantage of knowing, well, hell, a 3458 would meet, 0.01% DC voltage. Its end of period reliability would be as close to 100% as you could probably get,
right.
failure.
And now you've overbought, the specs are good. And now guess
Yep.
what? Assume you're doing your control charts every 3 months on the thing, or every 6 months on the thing. Now you can pull it out 2 years. So you're not without that for 3 weeks out of the 2 year. You don't have to have
Right.
that shutdown. You're only out three weeks every 2 years instead of 3 weeks every year, or whatever the lead times are all over the place anymore.
Yeah.
It could be 6 weeks down. But no, I mean, there's money to be saved that way too. But the engineering, I've seen it time and time again. I always have to, an engineer sees something, it's like, and it's like, I need to use that, but there's $200 in material over there. I need to use that, but till you draft it up, draw it, and whatever. So to phantomly use that $200, you're spending like 3 grand in resources and in resources that you never think about. I love that this point, because yeah, you're going to send somebody to school, you're going to hire somebody educated, you're going to hire a consultant and everything else. By the time you add up that $7,000 versus what, $18,000 meter or $20,000 meter, you're spending more than that $11 to $13,000 easily, just with time and costs on all of it.
Yeah. But what you're doing is really not, overbuying equipment. You're really buying you options. You're buying yourself the option to derate it, because you couldn't take a Fluke 87 if you spent $300 on a handheld 3.5-digit DMM. You can't take that and then assign a 10 part per million spec on it. It doesn't have it's just the wrong instrument. You don't
Mhm.
have that option. But if you overbuy, you have the option of derating it. And once you do derate it, your end of period reliability skyrockets through the roof. And that buys you the option of, if I need to extend it, if it's going to expire, but I got these super important measurements to get this lot of material out that I got to make over the next week, you feel super confident in extending the calibration an extra month or two to let you do it, knowing with super high confidence that there's no risk there.
Yeah.
So,
Well, that
yeah.
I mean, as a technical manager, it is uncomfortable when you're having to balance such fine lines, right? If you have an organization that you're a part of that is getting
Mhm.
you, erring on the side of the better standard, it makes it a lot easier to run your team. A lot less,
Yeah.
and or when customers call in and say, "Hey, can you do this?" A lot less investigation time, like to your point.
I have
Yeah.
a budget of $50,000, which is gonna allow us, if somebody's really knowledgeable, my budget's $50,000, which is gonna allow us to only eat $150,000 in rework each year. Versus if you give me $100,000 now, we're gonna eat about $10,000 in rework because we're humans and we make mistakes. But it's not gonna be the instrument's fault. It's gonna be our technician's fault.
For
Right.
real.
Yeah.
Well,
Yeah.
Henry,
So
we're getting close to the end of the time. Paul, I think there's thousands of things that we could chat with you about. Maybe
Yeah.
we can agree to another conversation in the future. But I
Absolutely.
want
I'd be
to
glad to do it.
I wanted to say thank you so much for coming on. I think this was I know it was enlightening for me, eye-opening for me, and you got to understand the people that listen to this, a lot of them are very new to the industry, and I think a lot of things that we talked about in these two episodes, these two parts, are things that people really find themselves conflicted about, right? Like things that come up and they're just like, how do I navigate these waters? I got two standards reading the same. What do I do? And I think we gave them some really good guidance today. So I really appreciate you coming on.
Oh, well, thanks, Ron. Yeah, and I certainly appreciate you and Henry having me there. And yeah, I love talking to you guys. And yeah, you bring up great points. And I think that young people out there that might be starting off, I always say, if we had figured everything out, we wouldn't have NCSL meetings every year, and we wouldn't have committees, and there's still a ton of stuff that new people that are coming into this that are just learning. You might say, well, I'm only a calibration tech. Yeah, but you got a fresh set of eyes that you can bring to bear on things that other people don't see. And there is a lot of things yet to still be discovered and worked out and figured out and managed. And a lot of it does have to do with the logistics of you mentioned technical management and stuff. It's like I said, you can figure out the optimum calibration interval and tell somebody this is the optimum interval, and you'll still have 95% reliability. And they can
Yeah.
say, yeah, but we don't want to incur that risk. We'd rather just
yep.
pay you to calibrate it every 3 months instead of 2 years. And we're totally willing to do that because on the off chance something happened at the end of 2 years. So management is a if you're into management, if you're into science, math, technology, and there's so many different measurement disciplines. You could spend your world in light measurement alone, or in temperature, or in force, or any one of these.
Any of them.
Yeah,
Control charts, but it just, yeah, I mean,
logistics.
like we
Yeah,
were hitting on there, Paul, if there's any like some good takeaways for people from me, control charts are one of my favorite takeaways from
ditto.
this discussion.
Absolutely. Yeah.
Though, but what else? So the Ryan mentioned young people, and you are the encyclopedia of you have, but for those that don't, Paul has 20 gigabytes of just metrology documents everywhere. This is his library. He's got an excellent system where he categorizes them by like what name, where it's from, the date. It's just that's a system where he can find things quickly. But if people are out there and they're like, what do I read next? You guys talked about TUR, you talked about control charts. Can you give them like in your like a couple of good things to go seek out?
Wow. Yeah, that's a great question. And every time that topic comes up, it makes us all think that maybe we need to do that. The problem is you get metrology guys together and say we want a 3-page primer introduction for new people coming in this field, and then we turn in a 100-page document. That's
Yeah.
inevitably what happens. But
Right.
yeah, I mean, I would say the best thing is there's always going to be your mentors at whatever company you work for, or this podcast is a fantastic outlet, I think, for people to know that there are resources out there. And what you're going to find in the metrology community almost by and large is people that really are passionate about what they do. And if I was sitting at my desk and got a phone call from a person that I had no idea who was and just said, "Hey, somebody gave me your name, and I just had a quick question. I was just wondering if I would, absolutely, take the time to help them." But as far as a reference document, don't start with the gum for sure.
No,
No.
or any
Don't ever
JCM
do that,
document. Decision
Yeah.
rules JCGM 106 is not your starting place. That is not, yeah.
Oh, come
Yeah.
on, guys. The gum is great.
Well, there's what NIST technical note what is that? What is it?
1297.
1890? What is it?
1297.
1297.
Yeah.
Okay, yeah.
1297.
I was gonna say
Yeah.
1897. I'd say you guys got it like that, 1297. But that's all RSS stuff. But it's good, it's easy, but that might not be the way you should do uncertainty. So I try to steer away from that. There's the NPL good practice guides. NPL has a lot of good guides. NIST has a lot of them. The papers are
Yeah.
everywhere, but they have to know what to look for. And we mentioned the
Yeah.
Eisenhart paper in the last one. That's a 62 paper. It's really freaking cool. But for the
It's
beginner,
long, and it's
yeah, yeah,
way too much for somebody that's
When
getting into it.
we
yeah.
recommend that you cast the M3003 to a lot of people.
3003. Yeah,
It's a
that's
good,
great
it
document.
breaks down like type B rectangular distributions really well. I like the resolution argument's almost like a rectangular, right? There's equal probability. Yeah, anyway. So what else that you have off the top of your head, one that you really like?
You're talking to me or Ryan?
Yeah, to you. I mean, I'll tell you mine. My for the people that are out there, I've been on before and plug these. It's Scott Mims. If you look up now I'm forgetting the title where the importance of definitions
Yeah,
is probably
TRTR. Yeah,
is
he
probably
does.
one of the absolute best ones. The other one I would like, it's starting to really, it's definitely in the top 5 on the decision rules is Paul's risk mitigation strategy, which we talked about today that Paul and John did. I think that's just such an excellent piece. I don't know if that's beginner level. It's more probably a little intermediate.
Yeah, I've had a ton of thoughts since we wrote it. And one of the main things that I was, told John when we wrote it, and John did fantastic work on it, but there's, I didn't want any formulas in there, right? Which sounds crazy, but there's so many papers, JCGM, all the Power Castros papers,
Yep.
all of these, things that are just, and they're great. We loved it. There's a NASA RP 1342 document it's a wonderful document. But they're heavy duty, and so
Yep.
I think it's important to try to, convey concepts via, words and pictures rather than, because a lot of young people, they're going to have various backgrounds. Not everybody's going to be a PhD in mathematics and stuff. And I'm certainly not, I am not a math guy per se. When I read Castro's papers and stuff, you take those and then you try to distill it down. So yeah, for I would say that the papers you mentioned are, Scott Mims' papers is good. There are some things out there that tend to be, I like pictures, I like graphics, I like things like that that explain concepts rather than, just getting deep down in the weeds of the, mathematics of uncertainty analysis. Can be kind of boring and
Yeah,
tedious.
especially if they don't know the statistics and what all the symbols, all the Greek letters mean.
It's
Yeah,
hard. Metrology handbook, the last one I was part, that's written rather, boilerplate, maybe beginner, but they have to buy that. I'm trying to think of what's free out there that
Mm.
they can get.
Paul,
yeah.
is there a good way for people to reach you? I don't want to put your email out there on blast unless you're open to that. LinkedIn may be the best way to reach out.
Yeah, absolutely. You can hit me up on LinkedIn anytime. Trying to think. Yeah, certainly.
Probably
We're
the
fine there.
least invasive.
Yeah, I think. Oh,
You
go
know
ahead.
what we should do, Ryan? I'm sorry. I just thoughts here for the listeners, and then it's going to put Ryan on the spot. We should do like a group page on either Facebook, link somewhere that people can join. I know there's the TMD group. I know there's the other group, but to just get all the like the people that have been on the podcast and the
Good
just the
idea.
that following, then they can pose questions because I know TMD is awesome, but you get a lot of with anything over time you start getting a lot of funny pictures and this and that and it just goes away from like some I mean people do get their answers but a lot of
Mhm.
times it goes less serious to, you know, here, look at this kid putting the penny in the
No.
outlet, you know,
And
that
I
type of
like it,
stuff.
Henry. So we have something called a Discord channel that we've never fully output yet. And I think this is the year that we will. Nice thing about that is that we can have a section for the memes and all that stuff, but then we can have locked or more controlled sections for people just trying to learn and all that. So good reminder. I'll work on that this year, and people listening can hold me to it if they haven't seen something in the next month or two. But hey, Paul, thank you once again. Henry, thank you as always. And
Oh, thank
uh,
you both.
I hope we'll get to have you on again, but this was a true pleasure. So thank you again.
Oh, thank you so much, Ryan. You too, Henry. Yeah, thanks for inviting me, and had a great time. Great chatting with you guys. It was always there. So yeah, much appreciated.
You
Awesome.
want to plug anything? What are you
Yeah,
working on?
anything to
What
plug?
paper you?
I don't know. No, nothing right now there. I would yeah, the one paper that is floating out there that's it's kind of a mouthful, but it's calibration and regulated industries, federal agency use of ANSI Z540.3 and ISO 17025. It's just a paper, and probably arguably it's just a little bit of history of the documentary standards of
I
calibration
love it.
metrology. And there's some appendices in there if anybody that is kind of new, if there's been papers that have been published, they'll be in those appendices. Again, it's a little overwhelming to look through there at all of that stuff, but the whole history of documents that have required, TAR, TUR, and that stuff is in there. But yeah, not working on anything really right now, but I got a couple things that I've often thought of. I think the adjustment thing is always, that's always in my mind. And
When to adjust. You
yeah,
had you did a presentation on it that was really great at NCSLI. And that book, for people that let's mention that again, Paul, because if they just want a general overview, the first 20 pages are that general overview of the history of all the standards and stuff. Really, I think they're the first, maybe first 18. Don't hold me,
yeah,
don't hold me to the exact number, but it's a short amount out of the 100 plus that
yeah,
Paul's written.
it's just a chronology or a list basically of these standards. And I think the reason that it's important, especially for new people getting into it, is that like we talked about in the last podcast, is that some of these documents are so obscure that you're never going to know that they exist unless
Yeah.
you don't know what you don't know. And so, and if you don't know, then then a new person could go out there and have these great ideas about how to find the optimum calibration interval and not know that RP1 and 35 other documents exist that have got excellent information in there, but they're really hard to get on a Google search. We live in
Yeah.
a society where we think everything you just do a Google search. 90% of
AI.
it, it's just
AI
not
will
going to
answer
work.
my
Yeah.
question. Good luck.
Mhm.
Not in metrology.
No.
No, it's getting better, but it's so wrong in so many things. But what was the name of just so they know again, because
Yeah,
it
it's
might have glossed
I
over.
think it's that's a hard copy, but it's calibration and regulated industries, federal agency use of ANSI Z540.3 and ISO 17025. And that actually is you can actually pull a copy off ResearchGate. There I do have like a PDF that's been updated, and stuff that's just not, but I continually kind of add to it. It's just my repository of stuff. But yeah, that's on ResearchGate. And if you just do a search for any of those buzzwords,
I think you
it'll
need to
come up.
sign up for that, but I'm on there too. It's a really good, if people are looking for things, questions, answers. Paul, you brought this up, so it's a good talk. ResearchGate, just ResearchGate. It's free. You sign up for it. You can search authors. You could search me, you search Paul, and then it'll come right up. You can subscribe to people so you know when they have new papers out. And ResearchGate does publish. There are a lot of good published metrology papers on there for people that are looking that you're not probably going to find with the Google search.
Yep.
So
We use it
Yeah.
for the school, and in creating the school, you have to have it. Yeah,
Oh,
you really
awesome.
do.
Oh, very good. Yeah, that's great. Yeah.
Well,
no,
thank you
that's
once
awesome.
again. And
I'm gonna quickly plug core values. I'm not plugging anything for the company, but if your organization does not have core values, I would suggest any management that's out there, any techs that are look up core values and start thinking about like what your company's core values are, because we did not touch on people, and people are the most important part of any measurement for the most part. And not everything's automated completely yet, nor probably will ever be where there's always going to be a person that's involved in the measurement chain somewhere. So having those people engaged and living and breathing those core values is essential to making better measurements. You buy the best equipment in the world, and unless you have engaged people, I guarantee you bad stuff will walk out that door, or you'll be doing a lot of rework if you have enough quality checks, and you'll be curious why, and it's because someone somewhere is disengaged and not looking over the things, as not checking the previous history, as back to the first episode. So
Absolutely.
look at core values.
Good perspective. Yeah. Thanks.
Perfect, Henry. All right. Well, and then thank you to all of you that have made this third season happen. It's because of you and all of you listening that we are having these continued seasons. So thank you once again, and hope you enjoy the season. And maybe we'll have Paul back on again. Thank you again, Paul. And
Yep,
thank
absolutely.
you all for listening.